give today I'm going to give a talk about work that Ron Lee and I are doing. We presented a preliminary version of this at PAA, which is probably on video, so you can compare. And today, time permitting, we'll present a little bit more than that, some extensions we've been working on. So Ron is live with us, but well, he's not live with us. He's remote with us at home, about a mile away. So I hope Ron will chime in when the opportunity presents itself. So this project is long in the making. We started thinking about this before the pandemic, I think in 2017, when life expectancy in the US had not gone down just 1 year, but had gone down 2 years, or maybe by then it had even gone down 3 years. And we asked the question, well, what would happen in the Lee-Carter model? Would we just see this kind of thing happen every once in a while with the Lee-Carter model? And is this nothing to get that excited about? We can't reject the null, which is that the world is just continuing in its usual random way. So that was where this started. And then, of course, nothing gets done quickly when I'm involved. Sorry, Ron. And then the pandemic came. And so now we have additional motivation for working on this, which is what's going on when life expectancy goes down, and more important, well, more centrally for this talk, what happens afterwards. Okay. So low mortality populations is meant to be kind of modern populations, like the United States or Japan or Sweden or France or Brazil, or and we're looking at what's happening when mortality goes down and what happens afterwards. So I think I've done the first part of this. I have an amazing tool here, thanks to Casey. When I shine at the screen, it shows you virtually also. So this is where we started. And then, of course, we have the COVID shock that's helping us motivate this work further. And so one question we'll get to at the end is about how something like COVID affects long-term forecasts, or should affect long-term forecasts. And what the first half of the talk, or maybe 2/3, will be mostly exploratory and descriptive. That's what we presented at PAA. And then at the end, I'll present, we're not presenting what we think is the model, but we'll show you some examples of how you could do something beyond the usual random walk, which is used with Lee-Carter. Maybe I should give a footnote here. The Lee-Carter model, which I'm going to call the Lee-Carter model, is two things, right? It's a decomposition of a whole set of age-specific mortality rates over time that isolates a single time index. And then in their original paper, Ron and Larry took the US and they said, oh, the random walk with drift works pretty well, so that's what we used. But they say in that paper quite explicitly that one could use any time series model for this univariate time series. And so even when I use the word Lee-Carter, I'm going to probably use it interchangeably with the random walk, but actually the other models we're proposing here would also, I guess, be Lee-Carter applications of the Lee-Carter model. Is that fair, Ron? Putting Ron on the spot? Okay, I'll take no answer as an agreement.
Yes, that's right.
Okay, so one thing to think about at the beginning here is that there are different types of mortality change. When I say change here, you can also think of evolution or development or change over time. So we have the long-term trend. For those of you who want things always in model terms, that would be like the D in the drift term of Lee-Carter. And this would be determined by technology, the rate of technology change, behavioral change, something like medicine, environment. These are all things that determine the course of longevity over many decades. Maybe we would even put in our biodemographic context for the really long term. Then we have the medium terms, and these are the things that we see that are maybe on the order of 5, 10, 15, 20, 30 years. These are kind of slowdowns and accelerations of progress. So for example, Sam Preston and many others have emphasized the role of smoking to changing these trends. We've had the cardiovascular revolution. Things like AIDS have developed over decades. The opioid epidemic in the United States maybe would also be this kind of long-term thing. I suppose obesity might fall into that category. New cancer treatments, if they arise, as they arise. And so this is also in the random walk with drift. That's the kind of the random part of the random walk. It kind of changes the trajectory a little bit over time. And then we have the short term, and that's what mostly we're going to be dealing with today. So these might be a heat wave, like in France. We have Magali, author of a wonderful paper on the French heat wave and how to interpret that. Cold, of course, is a big factor in mortality. We have flu seasons. Actually, that 3-year downturn we saw in the US coincided with a number of bad flu seasons in a row. It wasn't, there are a lot of things going on with a 3-year downturn. There was the opioid epidemic causing a lot of kind of steadily rising number of deaths. We had a couple of bad flu seasons, and then there's even other theories about cardiovascular kind of long-term trends that might have affected that. So that's the flu. And then, of course, since we started working on the paper, we have COVID. And the reason I have a question mark here is because is it the short term? Well, as I speak about COVID, I'll be kind of acting as if it's a 1-year shock, but obviously it's not 1 year anymore. It's now 2 years, and maybe we don't really know what it will be. Although I would say my best guess is this is going to be a short-term shock. It's not going to be decades. It's going to be single digits of years, but maybe that's wishful thinking. Okay. So I think I've said all of these things. This is the same slide, just with 2 things in red. These are trend changing, at least for a while. So that's kind of the random walk aspect of things. And this is the short term we're going to say is transient. And by that we mean that it doesn't have any lasting impact or has very little lasting impact. Okay, so let's look at the United States. We're going to be looking basically at post-World War II in a bunch of, we should call them just the HMD countries, but we're actually only going to look at the subset of HMD countries. So let's start with the United States. We see life expectancy at birth, rising from 66 up to 77 or so. You see that it's not just a linear increase. There are flattenings and accelerations. And there are also a number of reversals. So each reversal is done in a vertical line. And gray means the first reversal in a row. Blue means the second reversal in a row. And red means the third reversal in a row. Okay. So you see that 1-year dips are quite common. 2-year dips are kind of rare, and a 3-year dip is quite rare. Actually, in the whole, I'll show you in a minute, lots of countries, I think there are only 2 or 3 of them in HMD countries. And it immediately, starts, the statistically minded thinking, well, what should the pattern be like if these things were kind of randomly spread out? And so we can look at that in a second. Okay, so my next slide. So this is I'm going to show you now a slide that has tons of information. It's going to show you this panel for lots of countries, but it's the same structure of the slide. Okay, so here's our countries. I think there are 21 countries here. Russia and Iceland. I'm sorry, these are HMD abbreviations. So please turn off your mic and ask if I should explain any of them. To unmute and ask if you don't know. FRA-TNP, I think, is the French total national population. Yeah. Most of these are fairly obvious. Okay, and they're arranged in terms of the most 28 reversals in Iceland versus 6 reversals in Canada. So they're arranged in that order. Okay, and we see that even in a super fast, the fastest in the world increasing longevity country, Japan, you still have reversals. It's not, increasing fast is not a guarantee against not having any reversals. However, there are fewer reversals in some of the fast growing countries, although Portugal is also fast and there's lots of reversals there. So there's something else going on here. The small countries easily have reversals, just And we call this the Iceland effect. If you have a tiny population, you're going to get a lot of stochastic variation from year to year, even if the underlying rates are the same, just because of stochastic Monte Carlo random draw variation. So most of the talk, we're going to ignore Iceland because we kind of know why there's so many reversals in Iceland. Russia is its own case. There are probably people on this call who are experts and have spent many years studying just Russia, and we're going to basically just show the exception proves the rule. This is Russia is something different, which makes all these other countries something similar that we're going to try to discover. Was a question?
Oh, no.
Okay. So we're mostly going to be looking at these other countries. What else is the frequency of reversals linked to? So I think, but I'm not sure. It's slightly related to the steepness, but not very. And I don't know what else. So that's a good question. What else is the frequency of reversals linked to? So here's just, I don't know if you can see these. This yellow. These yellows are the 2015, 2016, 2017 period when the flu was bad in the US. And you see that many countries had a reversal at this time because it was a worldwide flu was fairly heavy. This is Southern Hemisphere. So no, New Zealand was not that year. Is Australia here? Is that Austria or Australia? I don't know. Oh, AUS.
That's Australia. Austria
Australia
is AUT.
So Australia and New Zealand, we're going to see in a few minutes, have very similar pattern of reversals, I think, if I can show the slide. Okay, so the point here is that there are common things causing these reversals, and we have some evidence that maybe this modern era is not just driven by medical progress and behavior. Maybe there are things, even before COVID, there are things like this driving the pattern. Okay, so here's the Lee-Carter random walk with drift setup, where we have this drift, which is that kind of long-term constant tendency for mortality improvement. We've got this random walk structure, which kind of shows fairly medium-term variations. And short-term variations don't happen very much in the Lee-Carter model because any change is then saved and gets cycled into the next change. So you don't just see a spike and then it disappears in the Lee-Carter model. Instead, you see a deviation from the trend, and then your new expected value starts from there with the drift. So we'll come back to that in a minute. But one feature of this model is that the increments epsilon are independent of each other. And so the chance of decline in any one year should be independent of any other year. And so if the chance of decline in 1 year is p, the chance of 2 in a row should be p squared, and the chance of 3 in a row would be p cubed. And if you look at the, we observed 200, this is now combining all the countries with different variances of epsilons and different drifts and all these things. It's a little bit complicated what this table is showing us, but it's all the countries together. And we observed 253 gray lines, 30 blue lines, and 3 red lines. But if this were following a random walk with drift, we would have seen about the same number of 1-year reversals, but many more 2-year reversals, and many more 3-year reversals. So what that's telling us is that actually our kind of standard way of thinking about this should predict a lot more declines than we see, multi-year declines than we see. Had it been super rare, had we found the opposite, then we would have said, oh boy, that 3-year decline that we saw in the US, that's really bad. That's really a departure from what we would have expected. But in fact, what we see instead is maybe the model is a little bit wrong, because we actually see many fewer multi-year reversals than we expected. Let's see. Yes, so that's just what I said. Okay, and interestingly, these ratios are kind of the same: 1/10, 1/10. So there's some structure there. We just have to discover what it is. Okay, so now I'm going to do the end of our PAA talk, which is now to describe the pattern of reversals in 3 dimensions, our usual dimensions in demography, time and age, and then of course geography, because we love geography. Okay, so for time, the question is going to happen: what happens after reversal? For age, the question is: does mortality change in a reversal look like mortality change in a non-reversal? A usual year when mortality is going down and life expectancy is going up, because that's the usual pattern in all countries except for Russia. And then for the geography, we want to know that little yellow line thing. Is there a way we can actually look for more evidence there and see what the pattern is across the countries? Okay, so for the question of what happens after a reversal, we're going to be looking at the kind of plots that I'm showing on the right. So to explain this is now France. We have French life expectancy at birth marching steadily upwards. 2003, we have Magali on the line. Was that the year of the heat wave, or do I have it wrong?
That is the year of the heat wave.
It is, yes. So this 2003 is the year of the heat wave. Actually, life expectancy didn't go down in that year. It just didn't go up like it usually does. So if we were doing
yeah, but there were 15,000 deaths, not 150,000 in 2 weeks. So there were about 10 times fewer deaths than during COVID in France.
I'm sorry, Magali, I can't hear you.
Oh, can you hear me now?
Yeah, no, it's just my ears. It's not your talk. Just say it again.
Okay, I was saying that there were 15,000 deaths during the heat wave. During COVID in France, they were nearly 150,000.
Oh, you mean COVID? Oh, yeah, right. So exactly. So this is not. That's an excellent comment in the sense that 15,000 extra deaths was enough to stop the usual progress, but it wasn't enough to create a reverse. And now Magali is saying that if had we shown this time series up through 2020, we would have seen 10 times the difference. Thank you. Okay, so how are we gonna look at this? What we're gonna do is we're gonna plot the change in 1 year against the change in the following year. Okay. And the crosshairs here are at 0, so they're not really centered around what usually happens. We could have put the crosshairs around what usually happens at the averages, but they're not. They're at 0. And so this is business as usual. This quadrant. This says life expectancy improved in year T, and it improved in T+1. Okay. This is saying, oh, we're having a string of bad years, really bad years, even worse than that 2003 year. Life expectancy went down in year T and went down in year T+1. And what we see actually is that, I'm sorry, and then we can ask kind of non-parametrically, what happens after a mortality increase, sorry, a life expectancy increase, and the answer is we get about a quarter of a year increase in the following year. But what happens after a life expectancy decrease? We get almost twice as much improvement the year after. Okay? So there's this tendency for things to bounce back. It's not like a regression with randomly distributed errors where you regress all the way to the mean in expectation. Instead, you go part way back. You get a higher than usual rate of improvement. And here's this curve here, this straight line here is just a regression line fit to these points, and R is the correlation here. And so you see that the value here is about the correlation here is about -0.4. In general, there's not a tendency for increments to be independent, as in the random walk model. There's a tendency for things to bounce back, for you to get some correction after each thing happens. There's also a little bit of correction over here. When you have a really good year, in one year, you have a little less good year the next. I shouldn't say good year, I should say rate of improvement, because these are steps. If you take a big step forward in time T, you take a smaller step forward in time T+1. Okay, other questions about what this figure is telling us? Because of course I'm not going to show all the countries and it's just become confusing next. Okay, we have a live audience, we can do questions. A live audience, and probably the remote audience won't hear your questions, so there's no reason to be shy. Okay,
Okay, so I have a question,
Yes, thank you.
but
Please.
maybe this is, I'm gonna ask it, but if you want to delay answering, that's fine. My question is,
Okay.
how much of this is due to harvesting?
So we think not much, or we can't detect much, which I'll answer later. Yeah, we can't detect much.
An alternative hypothesis is behavioral change, right? So the year after a bad flu season, we see more people getting vaccinated, for example. So are you going to distinguish between those, or whatever evidence you're using to say that there's not much
Yeah, so I think
harvesting would also
Yeah.
implicate not much?
our argument is a little more subtle. Because we're looking at differences here, what this is saying is that this is not a random walk. So you don't have to have, there's kind of the simplest explanation would be that, like, for example, if our true model were that mortality was a straight line with random noise attached to it, not random walk, then you would have very strong negative autocorrelation in the changes. So that's kind of what we're seeing here. And
But that's consistent with harvesting, isn't it? If you kill off a lot of the frail folks one year, then you're going to have fewer deaths of those frail people the next year. And so that would not be.
yeah, but I think the easier way to think about harvesting is with the levels itself, not the changes. But I'll say one word about harvesting later, yeah.
But how much
This
is
is
it
not,
due to?
this is not evidence, this is not strong evidence of harvesting. It's strong evidence of the random walk, not describing what's going on. This is the argument we're making. Okay, so basically all countries look like, most countries look like France. The exceptions are Canada and Russia, and a little bit the US. The US, you can see there's actually not much going on in the US. So it turns out, I think, maybe just it's coincidence, the country where the Lee-Carter model, the random walk, was first developed, it's actually not bad for the US, but it's bad most other places, at least in the sense that I'm looking at it right now.
Except Japan.
Japan is a little bit strange. This is, so there's a kind of technical note here. Lee-Carter works on K, which is this kind of more kind of linearized, at least for most, from empirically tends to be fairly linear. Life expectancy is quite curved in Japan. So really what we're seeing there is that big changes are followed by big changes because of the curvature. So it's because life expectancy is not very linear is the Japan story. And we could do this whole talk in terms of KT, but I chose to do it in terms of E0 because we know what life expectancy is. All of us know what life expectancy is, and only 70% of us know what KT is. Okay. And if I weren't speaking to a Berkeley audience, maybe it would be a smaller fraction. Okay, so sorry. So I don't want to say much about this. It's just that the French pattern is basically what we see in most places. Okay, so now let's look at the age pattern. About, I think, 80% of the cases are increases, and about 20% are decreases. So the weight attached to these two lines is quite different, but we see pretty dramatically different age patterns in the two kinds of years. This is the average, this black line here. So that would be in Lee-Carter language, that would, I think, be BX. And you see that in good years, the BX pattern is basically the same. And part of that's because 80% of the time, but it's also because the nature of progress is that we're helping out kids a lot of progress has been made on infant mortality, and not as much progress over the long term has been made on old age mortality. And so that's kind of the blue pattern is kind of the, this is one country, France, all the countries look a little bit different, is basically telling us the story that in good years, well, to a first approximation, it's a flat line. But in good years, kids do even better. And in France, I don't think it's a general pattern. In France, there's also good progress in people in their 70s. Okay, in a bad year, it looks like COVID plus accidents. So this is COVID right here, huge effects on the elderly. And I take it this is something else. This is France, and particularly if this was the US, we would say, oh, this is accident hump, accidents, opioids, things like that. But the big thing I want to point out to you is that the really strong effect in a bad year is on the elderly. And if anything, the strong effect in a good year is on the kids. Now, part of this, you could argue, I mean, we could have a formal demographic argument about, well, what are the weights we should put on different ages to drive whether life expectancy goes up or down? So part of this is a little bit mechanical, but I think even if we were to account for all that, the story is pretty consistent. In a bad year, the things that make the year bad are things like flu and weather, and those get the elderly disproportionately. And over the long term, we have lots of contributors to improving life expectancy, but a lot of them are for people at younger ages. Okay. So that's what I've said down here. Elderly mortality consistent with effects of infectious disease and weather. Okay. Now let's look at countries. I'm sorry, this is a difficult slide. What we've shown here are now the kind of departures from a smooth line through life expectancy, life expectancy over time. So you can think of these as residuals from a very simple kind of smooth fit to life expectancy. And when let's look at France and Germany. When France has a good year, so does Germany. And when France has a bad year, so does Germany. So what this says is that the correlation between France and Germany is very high, and in fact it's 0.7. And the correlation between France and Great Britain is 0.5. The correlation between France and Italy is just like with Germany, 0.7. And the correlation between, say, let's look at Germany and Italy, 0.5. Interesting. Okay, so there seems to be some patterning here. Okay, so this is I've plotted this in a way that kind of orders the table. I won't really talk about the ordering, but this is ordered in a particular method. But so the countries, if we order these in one dimension, this is the ordering we would get. And so in some sense, France is farthest away from Australia, which we now know is Australia and not Austria. And the pattern is kind of makes sense. Countries that are close to each other have high correlations. I don't know what a negative correlation is. Sample size is small here. This is just 50 or 60 years, so that shouldn't be taken too seriously. But you also see some interesting patterns. Okay, it's not surprising that the US and Canada are very highly correlated. But to me, at least, it's surprising that Australia and Canada are very highly correlated. They're in different hemispheres. What's going on here? Well, I think the answer is kind of from an infectious disease point of view. There are probably people traveling, disproportionate number of people traveling between Australia and Canada, or somehow the contagious networks are that way. You don't see a strong relationship between Canada and Japan or Canada and Taiwan. Okay, but you do see a strong relationship between, say, Japan and Taiwan. So there's another puzzle here. We're not going to answer the puzzle and say what's going on here, but there's definitely a geographic pattern to these shocks, and it's not just that countries next to each other have the same weather. It's also that people are traveling between them. Now, a third hypothesis is that there are different kind of cultural health regimes, and that Australia and Canada are somehow similar. And so they have similar reactions to shocks, but I don't know what shocks would happen simultaneously in Australia and Canada.
Josh, what are you going to do about comments in the chat?
If you see one that is about now, then please ask it.
From Mike Murphy,
Yes.
acquired immunity in bad years would lead to lower mortality in the next year, with effects most concentrated among older people. So that it's a different sort of.
I think this is the same as the selection question qualitatively. It's a different aspect, it's a different angle on it. So I'm punting that for the moment.
Okay.
But it's a good point. Yeah.
And then the other one is, how would these trends look if we use mid-year to mid-year annual data?
Excellent. Yes.
Calendar.
Yes.
That's also from Mike Murphy.
I think that's, I would love to do that. Magali, Carl, can I do that with HMD?
No,
No.
Mid-year to mid-year?
Yeah. So actually, Australia would be a good one because presumably the flu season is mid-year, as opposed to and that's the interesting thing about that is that the negative autocorrelation we're seeing between changes in years is actually probably too low because there's this kind of automatic correlation of weather and flu season that goes from December to January. Although I don't know, my sense is that often things happen in one year or the other. So I don't know the extent of that, but super interesting question. In theory, one can answer this using the short-term mortality data set and things like that, which has monthly.
We also have the deaths by triangle, exposures by triangle, so you could get some approximation of mid-year based on that.
Thank you, Mike, for volunteering to investigate this.
Let me add, in historical demography, almost always one tries to use harvest year data, like from September 20th to September 20th, something like that. And that makes quite a bit of difference. But because that's when prices would be high or prices would be low, and that has an influence on mortality. But it might make less difference today. I think it would be. I think there's less seasonality in mortality today than there used to be. That's all I wanted to say.
Yeah, and I think then, especially when we're thinking about the shocks, do they typically go over the New Year's Day type of thing? So that's not just the seasonality of the general trend, but rather for these deviations from trend. Okay, and in the paper, I think we have this for 19 countries, and it's even more interesting, but that is even more unreadable. Okay, so now I'm done with the PAA talk, and now I'm going to do what we've been working on since. If the random walk with drift isn't the right model, what are some examples of things that might make more sense? So here's, in the paper, we look at two types of things. One is more kind of a ARIMA approach, and this one is referred to by structural time series is one label for it, or state space modeling, or there are probably other labels too. And it's going to be kind of, there's going to be two layers to what's going on. There'll be a kind of underlying latent trend over time, or evolution of mortality over time, which is going to be the random walk with drift, which we already saw. And then on top of that, every year we'll get some random thing, which is this NT, which are now going to be really independent each year. But we're going to get a different NT. And the reason the letter N is used in the literature is because it's thought to be kind of noise. And these models are sometimes used, I think you learn about them when you're in the at West Point, and you want to fire on a tank, and you look at your screen, and it says where the tank is, and you want to aim for the tank, and you see the tank moving, but your radar isn't very exact. So it uses like a Kalman filter or this kind of model to say where it really thinks the tank is, because it gets to see it multiple times. And each error in the radar is assumed to be independent. Okay, so that's what's going on here, except we're not thinking that this is some kind of error, this MT. We're thinking this is actually the interesting stuff. This is COVID or a heat wave or a bad flu year or whatever it might be. What else do I want to say here? So, of course, this is latent, so you need some fancy statistical machinery to estimate these things, but you can estimate this, and when you estimate it, you get a drift term for the latent process, which is what you want to use to forecast. You get the variance of the innovations for the latent process. This is the same as in the Lee-Carter type of formulation. And you get how much noise is there on top of this. The noise that we're interested in is we want to take seriously, and so we get a variance for this noise. Okay, I'm very happy to take a question. It's probably either too much to digest, or you already have seen this, so there's probably very few people in between. Okay, let's look at what happens when we fit this model. So this is just a note. Okay, so we're doing this again for E0, which is not the way one should do this. We're just doing it for explanatory purposes. You should probably do this on KT. And here's what it looks like for, I'm taking again the example of France. The latent process just looks like a smooth version of what we really see. And then the NTs here are these little deviations from the red. the gap is the NT. Okay, and so zoom in on 2018. I can't really do that, I don't think. No, I can't. But if we focus here on 2018, I wonder how I even have this data for France 2018. Oh, I think 2018 is the last year here. But you notice that they're not exactly the same. It thinks that 2018 was I think a slight flu year in France, and so the actual latent level of life expectancy was a little higher than observed. And we can look at 2003. Well, the latent thing doesn't even think that that the heat wave happened, because that was just a transitory blip. That was just NT. Didn't affect at all the underlying process. So here's what the coefficients look like when you compare the two models. Same drift, essentially. I'm showing it to 3 digits just to show it's not exactly the same. In the Lee Carter, those epsilons have a standard deviation of 0.3. And in the structural time series, that's pretty much divided up. Half of the variation is the kind of process variation, the variance of the epsilons is about half of what Lee Carter thinks it is. And the other half is just this transitory stuff, which is about equal in the case of France in magnitude. And blowing in the wind here, the screen. For those of you doing remotely, you have the advantage of not getting seasick because your screen is stationary, but ours is being blown around by our open windows and our ventilation here, the great ventilation we have among the department. And
That's the NT.
That's the NT, exactly. We're getting some random shocks on the screen. And exactly, and the people on Zoom are seeing the latent KT, which is exactly. Thank you, Ron. Okay, so what else do I want to say here? I think that's pretty much it. Oh, I guess from a statistical point of view, the model fits better. If you want to take that, it's better than fitting worse. But I don't think we want to say that therefore the model is right or anything like that. Oh, and here's the one thing I was going to say about selection column. You can look at those NTs to see how they're autocorrelated. And that's how we're thinking of this selection, which was mentioned by Will, or the immunization, which was mentioned by Mike Murphy. That we think in this setup will be seen in the correlation of the NTs, and we see none to speak of. I have some other work I'm doing on the size of these effects, where we're arguing that they should be very small, or that there's good reason to think that they'd be very small. They could be detectable in some cases, but they're going to be very small in magnitude to the shocks. But that's not, I'm not showing any evidence for that yet. Okay. So here's an interesting outcome of this. For France, again, this is not the way Lee Carter would do this, because Lee Carter would work with KT rather than 0. But the Lee Carter forecast would be these black lines. And the structural time series, because it has much smaller kind of process uncertainty that accumulates, actually has a much narrower confidence interval. Now, when I saw this, I said to Ron, oh, this is really bad. We don't believe that we know more about the future than we thought. In fact, we think we know less about the future than would be in any specific model. And Ron replied to me, well, actually, if you, in his work with Tim Miller, they find that the confidence intervals, at least in the short term, I think the first 10 or 15 years, are a little bit too wide. In other words, so there's some empirical evidence to show that maybe these red confidence intervals are not crazy. But that's one implication of this model, is that we're overestimating when we do the random walk with drift, how much uncertainty accumulates over time. Yes.
Zero comment from Johannes. Why not including a parameter to estimate short-term autoregression in the model? In the case of COVID, this might make sense. And then Ron, I think, just answered.
Oh, great.
Yes, that is sometimes done, or more generally, AR IMA models. We consider more general models for the US. but the simple random walk would work best here.
Yeah. So it could completely be done. That would be a next step. And I think the problem that Ron is pointing out is that all these time series are very short, and each country is a little bit different. So I suppose one could pool all the countries and do some kind of general model and get some leverage off of them. But any particular time series of 50, 70 years, you don't have a lot of ability to distinguish between these models. So that, I hope, is one of the contributions to this paper, is that we're kind of slicing it in various different ways. We're not taking a super statistical approach here. We're kind of taking a more qualitative approach. So we're using that to kind of hone in on the kind of qualitative nature of the model here, whereas kind of a goodness of fit or a statistical approach might, it leads to a different thing in each country. It's very sensitive to things and that sort of thing. Okay, what's another implication of this? Another implication, again, I'm totally reliant. We're totally reliant on HMD here. We could probably do other things if we weren't. But I looked at HMD 6 months ago, and Portugal already had 2020. So they already had one country with the pandemic. Now there are more countries. And so this is now Portugal. And I'm not showing the confidence intervals, I'm just showing the central forecasts. So the Lee Carter starts from the last point because it thinks everything is cumulative. You don't forget anything. The structural time series says, oh no, this last point, that was a blip. I don't want to start from there. I want to start from something more like where I was the last few years. Okay, so it has a different intercept, a different launch point. And I think this makes total sense. I think if the Census Bureau or Social Security or any forecasters are not starting their Lee Carter forecast with 2020 life expectancy. Instead, they're assuming that COVID is somehow going to disappear over time and that we should start with something previous to that. And here, this is kind of formalizing that. The other thing that's kind of interesting is that because the drift is estimated on the latent process instead of the observed process, the drift doesn't think this decline matters for the long term. And so the drift of the red line is slightly higher, the slope, than the black line, and they diverge slightly. So that's, again, kind of second order effect, but it's kind of another reason that you don't want to apply the random walk with drift too literally when there's a shock.
So just to go back to the prior slide on the forecast interval, so Carl Schwartzman asked the question, forecast intervals are narrower in the new models because in the original Lee Carter model, 100% of the shocks are remembered and built into the future. Well, here about half is forgotten. Is that right?
Absolutely. Better said than the speaker himself. Thank you, Carl. Okay, so we're done essentially. Okay, so here's some things that people can work on. Some other things were brought up here. So, is the true uncertainty really so narrow? Yeah, I'm sorry for not clicking consistently. Okay. I said that we're interested in the NT because they're real. It's not just random noise, but actually some of it is. Some of these countries are small. Portugal is small. Iceland is really small. So I think one might want to try to distinguish between that, which should be possible since we know the size of those countries, and we could just have a statistical model that told us how much of that NT would be attributable to finite population size and how much of it wouldn't. Another challenge is understanding why some countries like the USA don't have transient shocks in the sense defined here. When you estimate this model for the United States, the variance of NT is 0. It thinks the random walk with drift is the right model for the United States, as Ron and Larry found when they looked at this. In the Carter model, we have 1 BX. So now I have kind of a more complicated KT here, and these 2 levels of KT. Well, one might also want to have 2 levels of the BXs. Again, I don't think that's going to make much difference in the forecast, especially since one of these is forgotten. But kind of for conceptual clarity and thoroughness, one might want to think about that, right?
John,
Yes.
let me just add that how you approach this will depend in part on what sort of forecast you're trying to make, for example. If you're interested in longer term forecasts, it may be the random walk with drift works well. If you're interested in the shorter term variations, which you might be for some purposes, sometimes people are even interested in quarterly projections. Well, then these differences in the age distribution of mortality shocks and the bounce backs and all of these things become much more important. I just wanted to insert that. You can go ahead.
Thank you, Ron.
But just building on that, I would think that it would depend also on what the nature of the shock was. So to what extent can you actually categorize, do you think this shock is due to heat? Or do you think this shock is due to opioids and war, in which case there may actually be some permanent component and random walk with drift may actually make more sense?
Yeah, so I think there's this kind of two opposing purist perspectives, which are clearly both wrong. One is we see nothing but the data. It's just it just emerges to us. All we have is HMD. We don't know anything else about the world. We just have these time series, and what do we do with them? And that kind of keeps you honest in some sense. It stops you from kind of chasing some story. And then there's the other side. Well, we know it's COVID now. I think our prior on 2023, 18 months ago, would have been there's going to be no COVID mortality in the US. But now our prior has changed. So the fact that we know something about this should influence our forecasts. And somehow the right way to do this is to combine the right amount of knowledge from both and not to over guess. I think part of what went on when we saw this mortality, the life expectancy in the United States, is people will point to all kinds of specific causes. It's because of our healthcare system. It's because of increasing inequality. It's because, well, actually, this was because there was a fluke. It was two things. It was our increasing opioid mortality, which made us already increase mortality improvement very low, plus the worldwide shock of a couple of bad flu seasons. So I don't know if we would have. I mean, that's my interpretation now after kind of working through all of this. If we only focus on that narrow one country, one time period, we have lots of stories, but not much evidence. If we go much broader, so I think Ron keeps emphasizing this in a real forecast, especially on this launch point thing. You know something about what's causing things. It wasn't just you don't just have a list of numbers. You know something about the world, and you should take that into account when you do the forecast. And clearly, this model is set up. NT is serially independent. It doesn't allow for a 2-year COVID shock. That's not in the model. So it's certainly wrong to take it literally.
Maybe you want to, so Ken has a comment question.
Yes.
Maybe Ken can actually say this question.
Ken, I have one more slide. Do you want to go now or do you want to, yeah, let's have your comment now. That's fine. Yeah. If I already knew what the next slide said, you would break my concentration, but I have no idea what the next slide says. So now it's fine to have a question.
So I can read his comments. Do I understand that you model the whole of KT with latent plus noise process? So you're not allowing for the noise shock process to have the different age profile that you talked about earlier?
In the specific example we're not even doing Lee Carter, we're just doing life expectancy, E0. So there's no age at all. It's just a series of numbers, univariate time series. In applying this, you could do it with KT with one schedule, or as I discussed earlier, one might want to do it with 2 different schedules. Or you could even go further with Will's idea, which is that you know the nature of the different shocks. Each different type of shock has maybe a different age profile. One could do it that way. So it's kind of a continuum of possibilities. I know that it would be nice if this paper we're offering, here is the new method you should use. But actually what Ron and I are doing here is much more modest than that. We're just trying to develop some qualitative ideas for these models. And it turns out that there's an enormous literature, which Ron knows much better than, which I don't really know at all, but Ron knows quite well, which is different types of ARIMA modeling, machine learning, all these type of things for all these different countries. There's a multi-billion-dollar financial instrument market in mortality traded about these longevity bonds. So there's a lot of people working on this in much more sophisticated ways than we are. Okay.
We're trying to bring some demographic insight as opposed to just the statistical modeling.
Good. Okay. So our stylized facts are transients. Most reversals are followed by a bounce back. Age, it's true that what goes up does not go down. There's two different things going on. And neighbors, that this kind of spatial correlation pattern is quite interesting and would be very interesting for others to investigate further. And then in terms of modeling and forecasting, these stylized facts are not consistent with, here's an example of my mistake that I said I would make with the Lee-Carter random walk with drift assumption that all change accumulates. They appear to be truly transient effects, or at least partially transient. For forecasting, we should start with some estimate of the latent level rather than the last observed. So the structural time series gives you one way to do that. I don't know how good the last level is. The structural time series actually, different ways of estimating it, kind of fills in once it knows the future. It goes back and adjusts the past, depending on how it's done. So this is where knowledge and judgment could come in, what you want to do. Structural time series is a good place to start. I personally have grown to like it because I think it tells a nice story. I don't know much about its actual forecasting properties. Ron also just a couple of days ago suggested a different way to do this with more standard ARIMA models, and that's now in the paper. But it's not. It doesn't tell as good a story, although it has very similar and desirable statistical properties. There's also a place for local knowledge, e.g. COVID right now. And then, of course, there's lots of opportunity for future work. Culling and selection is obviously a big hit. People want to work on that, please do. Multi-year shocks, now that we're in 2 years of COVID. The age pattern example that Ken talked to, and more. So that is my last slide. We've already had lots of discussion. It's now 1. I think we're not doing a meeting with the graduate students afterwards, so we have until 10 past. So we can take questions until 10 past, or if people mostly ask their questions, we can stop earlier. Okay, I have a question from Lisa in the room.
I don't know if we talked about this at the beginning. I heard you mention the Spanish flu of 1918.
Yeah.
As a shock. Did you talk about the fact that 2 world wars would have had more of an impact on the civilian population in Europe? Canada would have sent soldiers, but we would have had such a large. So I was trying to figure out why Canada is at the top left corner.
Ah, okay.
Each time had fewer reversals, and then I think then that must be linked to the fact that there's another one.
Okay, so there's a lot here. I'm going to answer your question, but this particular slide only goes back to 1950, so it doesn't show the Spanish flu. But rereading the original Lee-Carter paper, I was very struck by the fact that they see the Spanish flu as a problem as a modeling challenge. And there's a very explicit discussion of what should we do with the Spanish flu. And so it's interesting to go back and look at that. What they decide to do is essentially put in a dummy for it and say, our model is not meant to cover that. We're just going to have another parameter that deals with that. But they also discuss and say, another way to do this would be to include it as part of the process if you think that the Spanish flu is something repeatable. Okay, well, the first 63 times we each read this paper, we thought, oh, it was a good decision to use a dummy. But all of a sudden, the 64th time we read it here in 2022, it says like, oh yeah, I guess this is part of even 21st century mortality, these pandemics. But then your point about soldiers returning, I guess, is more to a little bit connected with when I showed this this picture here, where you have Australia and Canada with a fairly high correlation. Let's see, how's Australia and Great Britain? Well, it's not zero, but it's not very strong. But there's something going on about international travel is one possibility of what's going on.
Of course, all these correlations are going to bump up a lot when you can do them through 2021. And they include
Yes.
COVID mortality.
Yes, I think this is through 2013 or so, because of the nature of the HMD data. And also at one point, we were kind of setting aside the recent decline as kind of out of sample. We didn't want to include that. We wanted to look at the past before that. Other questions from the room? Yes, please.
From my understanding, does it make it more important than to determine whether a shock is truly like the time series nature of it to apply the correct or most accurate model? Because some things that are longer term, like the AIDS epidemic, will need to be maybe used a week harder, but something that is deemed truly short term needs to use maybe this new empirical time.
That's what we're proposing as a possibility, that you could have a model that has both of those things in it. You don't need to choose. In this setup, you have both, you know, the kind of medium term deviations through this epsilon, and you have the transient one. So both are happening at once. When you fit this model, at least the way the algorithms that we've been using work, it doesn't know anything. It just sees the data and figures it out itself based on the structure of the data. But I'm sure there's lots of room for adding structure, and this is done. The way we're doing this right now is just with a simple kind of common filter type approaches, which are built into statistical packages. But you could also do this in like a Bayesian framework, where you would add a lot more structure, and then I'm assuming the parameters could be estimated, but I don't know. Are there other questions from the audience?
There are a couple.
Okay.
So Carl Schwartzman had suggested that presumably the new model fit for Iceland has a much higher sort of transient variance, latent variance, so it will favor a smoother latent time series for a small population.
Yeah, and I think something maybe to investigate for us is to, I think one could hypothesize that the epsilons would be the same or independent of population size, the variance of the epsilon. Oh, sorry. Because the underlying process in these countries, I mean, I suppose there's some degree of size. The United States has different populations that might cancel each other out a little bit, but that's right. The NT variance would be very different, depend very much on population size. And maybe the epsilon would not depend much on population size. That could be something to investigate.
Hey, Carl, did you want to follow up on that, or?
Well, as Josh was saying it, I was thinking maybe you want NT to be something meaningful, the way you were interpreting it before. But if you're doing more smoothing in Iceland because you've got a big NT, then NT is really just sampling noise. So I don't know. I'm ending up a little confused about what's
So yeah, so
NT would be.
I do have a thought on that, which is that NT is a combination of the two. And since we know something about the size of the populations, we should be able to actually break it into two and have it be something additive, which is an additive effect due to finite sampling size, and an additive effect due to what we're really interested in, which are these kind of transitory shocks. Does that? For your next
There's a
Bayesian-
whole
for your next
there's a
Bayesian
whole
workshop-
literature.
Please, Ron.
There's a whole literature on calculating these small population contributions to variance in births and deaths and population growth and so on, which could probably be drawn on. I also wanted to just make some comment on the difficulty of the age distribution problem, since as we know, in the Spanish flu, the big increases in mortality were during young adulthood, whereas with COVID, the big increases in mortality are in old age. And it's it's not easy to find consistent, common patterns and figure out how to deal with them.
And Ron well, maybe Carl, do you see this as a tractable problem to separate the two? The kind of population size effect from the something else, which we're calling the transit shocks?
I would say yes. I mean, we know what the age-specific populations are in Iceland. We can probably model the noise.
Great. We have a question from Carl in the room.
Yeah, I was curious whether asymmetric white noise would in some ways be able to model the same type of thing as your NT.
Yeah, so this is now just using all the standard assumptions of normal deviations, normal noise or innovations. You could certainly, if we were in a Bayesian framework, we could specify.
I'm saying,
we could specify something else.
Up three times as much as
The other was, I think, what I'm thinking is that maybe there's the little variations which we don't think are caused by the same thing as big. Maybe this is not kind of thin-tailed like the normal is, but maybe it's fatter-tailed because the big deviations happen. They happen infrequently. When they happen, they're quite big, or something like that. Again, the data, it's probably difficult to answer these questions from a statistical point of view, but one could try it and see if there's evidence for one thing or another. Okay, let's stop here. Thank you all for such great questions, both during the talk and after the talk. And thanks everybody for joining in from so far away. Next week we have Sam, the last name is Trejo, who's from the University of Wisconsin. So please join us. We'll be 100% virtual next week. And if you like the hybrid format, tell us, type it in chat. If something was horrible or we could fix, please tell us, we'll try to fix it. Do we have other we have other local speakers during the semester, so we have the chance to do this again if we get good feedback. And thanks everybody for your attention. And please
Thank you, Josh.
write email. This recording is now ending or something like that.